Hello everyone. Welcome to Module 5, the mole. This is perhaps one of the most important modules of the semester because the mole concept will be very important in several of the remaining modules. So please take your time, make sure that you completely understand this concept as you go through. And feel free to keep rewatching these videos as much as necessary until it sinks in. So the first section is section 5.1, moles and atoms. So the learning objectives here, understand the mole concept, convert between moles and atoms, or vice versa. To start with, I actually want to have a review question related to the things we talked about earlier, and we'll see how this relates to what we are talking about today. So go ahead, look at this, maybe pause the video, try to solve this problem, and then we'll be back with the solution. Okay, so here's the question. How many nails are there in 1.75 pounds of nails if 1 dozen nails weighs 0.15 pounds? So I'm going to start writing down some information and then we will solve the problem. So we know we have 1.75 pounds of nails. We know that 1 dozen nails equals 0.15 pounds. We are looking for how many nails. Okay, and there's one additional piece of information here that you are not given. I'm sorry, let me move that over so you can see that. There's one additional piece of information that you're not given, but you probably already know, and that is, what does the word dozen mean? So if you didn't know, 1 dozen nails means you have 12 nails. Okay, so we all know that. We all know what a dozen means. But we need to have that information in order to solve this problem. Okay, so we have, this is our question. I kind of put that in the middle there. It might be easier if you had put that perhaps at the start or at the end. We have 2 equalities. We have a number by itself. When we solve these kinds of problems, it's always best to start with the number all by itself. So the 1.75 pounds of nails. So we will start there. So we have that information. And then we use our equalities to come up with a conversion between pounds of nails and something else that might be useful. So we see right here that 0.15 pounds is equal to 1 dozen nails. So we'll go ahead and do that. So we'll say 1 dozen nails on the top and 0.150 pounds on the bottom. So we've used that. I'm going to just put a check mark so we know we use that one. And then we use the definition of dozen. So we have 12 nails on the top and 1 dozen on the bottom. Okay, so we've used the information. Let's see if this works. So we want how many nails. We're showing nails here in our last step, so hopefully all our conversions cancel, and that's what we get. So the dozen will cancel, the pounds will cancel, and it looks like that should work. So we multiply everything on top. So 1.75 times 12, and then we divide everything on bottom, so divided by 0.15. If we do the math there, you should get 140 nails. Okay, so I want to talk a little bit about significant figures here. When we have the 1.75, we have 3 significant figures. When we have this conversion, we have 3. 12 nails in a dozen, that is an exact conversion. There's no uncertainty about that one at all. And then you might be thinking, well, you know, why do you need a decimal point if you're counting? So can we have 139 and a half nails? Can we have 140 and 2/3 nails? No, we have to have whole numbers of nails. However, we did not actually count these nails by hand. We counted these nails by these conversions, by finding the mass and using these conversions. So when we report this, although it looks like maybe we are counting, this is still a measured number. Okay, so we do include significant figures for that reason. You could take those nails home and count them and find out that you only had 139, and that would be consistent with what we're showing. So that last digit is somewhat uncertain. The ideas we're illustrating with this problem are the very same ideas we'll be seeing in this module. So everything we do here, we'll see how it is analogous to things we'll be introducing. And in fact, in this first module, we will only basically do one of these. Okay, so back to our PowerPoint. What we're illustrating with this idea is something called a collection term. So a collection term is a word that represents a specific number. So we know the word dozen means 12. Other examples, the word ream means 500 when you're talking about pieces of paper. The word case means 24. 24 cans. So we are familiar with this idea of using words to represent numbers. The mole is one of these examples. The mole is also a collection term. The mole is a word that represents a number. The definition of this number, so we're going to start with the definition and then we'll see what the number is. The definition is the number of atoms in exactly 12 grams of pure carbon-12. Okay, so that's how we define this number. The number itself is here. This is Avogadro's number, 6.02 times 10 to the 23rd. This is a very big number, and we'll talk about that here in a minute. But a little bit more about the definition. The way this works is that we can use the definition of a mole in order to count atoms, essentially by weighing them, as we'll see. Okay, so when we say we have 1 mole of atoms, that means we have 6.02 times 10 to the 23rd atoms. Similar to how we would say if we have a dozen donuts, we have 12 donuts. We understand the word mole to mean this very large number. Now, how large is this number? This number is so big that we actually don't quite understand how big it is. I'll give one example of how big this number is. If we had, say, 1 mole of dollars and we had to spend them, we just had to somehow use up all that money. And if you started spending that money, so let's say you were born with that much wealth somehow, if you started spending that money and you spent it at a rate of $1 billion a second from the time you were born, until you died at the age of around 60 to 65. And you did this whether or not you're awake or asleep, regardless of what you're doing, you're somehow spending $1 billion a second. You would have only gone through about 1% of your money. So that's just to understand how big this number is. Okay? This number is so big we can't even really comprehend it. It's just a really big number. And that's something that will affect, as you'll see, how we talk about this number when we use it for counting things. Okay, so remember this equality. We're going to be using this equality on the next slide. Okay, so another example. I'm here using this mole concept. Go ahead again, maybe pause your video and take a minute, see if you can solve this. And sorry, a little interruption there. See if you can solve this, pause your video, and then come back and we'll go through the solution. Okay, so let's go ahead and try to solve this problem. So the number we're given one number in the question, 1.89 times 10 to the 20th aluminum atoms. That's what we're given. The question is, I'm just going to write question mark, moles of aluminum. That's what we're looking for. This question is essentially like saying you have, 45 donuts. How many dozen donuts do you have? We're answering this based on understanding the collection term. So the collection term here is 1 mole is equal to 6.02 times 10 to the 23rd atoms. Okay. So essentially the only difference is we're dealing with a number we don't understand here compared to a number like a dozen that we do understand. But what we want to do, we want to use the same process where we let the units do the work for us. So we say, we start with a number by itself. So this number of atoms. And then we set up a conversion factor based on what we're given. So we want the atoms on the bottom. And we want the moles on the top. So that's how we set it up. So that's part of this, is understanding how to set it up correctly. The other part is doing the math. I'm going to go ahead and show how we can do this math. I'm going to use my phone in this case. I think I had an example earlier where I was showing this with a regular calculator, but I think most of you are familiar with this. So I'll go through this, and then we can look at your own calculator if you are having trouble getting this answer. So we have 1.89, and then for scientific notation, this is how this works. You press that button, so EE, and then 20. Okay, so that's putting it in scientific notation. You press the button one time, you don't put times, you don't put 10. That one button does all of that for you. And then we do divide, and here we'll do Avogadro's number, so 6.02, that one button, and then 23, and then equals. Okay, so that's our answer. I'm going to write it down the way it's shown there, and then I'll put it in scientific notation. We want 3 significant figures, so I'll do that. And then for scientific notation, we have 1, 2, 3, 4. So we would write that as 3.14 times 10 to the negative 4th moles of aluminum. So that is how we would do that one. If you're not getting that exact number, if you're getting something that's off by a factor of 10, so if this exponent is incorrect, you want to make sure that you know how your calculator is doing this, and if you have questions about that, feel free to bring your calculator to me when we meet for lab this week, and I can take a look at it for you. Okay, the last thing we want to look at here, as we do these calculations, we can ask ourselves if the number makes sense. And there are, when we're dealing with a number this big, there are some very easy ways to answer this question much of the time. If you're counting atoms, you should have more than one atom. If you have 10 to the minus 2 atoms, that does not mean anything. There's no way with this kind of calculation to have less than one atom. So make sure that you are getting that. If you are getting very large numbers of moles, that doesn't make sense either. So if you have, say, 10 to the 24th moles, that is about the same amount of stuff as there is on the moon. We're not dealing with matter that large in here. So just be on the lookout for that as well. If you get extremely large or extremely small numbers, that you want to be careful of that. So 10 to the negative 45, that is not possible. Things are not that small. And we actually know that scientifically, and we'll address it a little bit in a later chapter. If you get 10 to the 45th, that's about as many moles as there are in the Milky Way galaxy. Okay, so numbers this large don't mean anything either. With the type of calculation you're doing, you're probably going to be able to ask this question and know if you have the right answer. because if you do it backwards, you'll end up getting either really too big or really too small. Okay, so that is it for this subsection. Go ahead and complete worksheet 5.1. If you have any questions related to this material, ask them on the discussion board, and then when you're ready, proceed to 5.2.